Balancing redox reactions is kind of the capstone of all of this chemical reaction information we've been learning. It's applying a lot of it to do something fairly difficult. This first example is sample 4.19 from page 165 in your text. I will tell you that the rules are slightly different if it's an acid or a base. So I will either tell you it's acidic or basic, or I'll give you some very easy way to identify which is which. The first step, regardless of which it is to write it into Net Ionic Form. I'm going to often give it to you that way, and you can look at this one and see that it's already there. But remember that that is the first step. You don't need all the spectator ions in the way. The next step is to write it as separate half reactions, the reduction reaction and the oxidation reaction. But in order to do that, you have to assign oxidation numbers so that you can see which element is being reduced and which is being oxidized. So let's start there. Our hydrogen ion has a charge of +1, which means that it has an oxidation number of +1. Ions are relatively easy that way. For this dichromate ion, the overall charge is -2, so we know that that's going to have to be our overall total charge. Oxygen is going to be -2. If we have 7 of them, that gives us -14. But we want a charge of -2. So that means we need +12. So each chromium has to be +6. Let's look at the next compound. Our oxygen is still -2. And our hydrogens are both +1. That gives us -2, and we'll make just little notes over here. And then +6, because there's 6 hydrogens. That means we have a total of +4, which means our carbon has to provide -4. So each carbon is -2. Our chromium ion is +3. Oxygen here in this carbon dioxide is -2. That gives us -4. So this carbon has to be +4. It's a pretty big change to go from -2 to +4. In water, we've got -1 and +2. Water is almost always just going to be bystander, but we're going to go ahead and label it. Now let's identify oxidation and reduction. Our chromium over here is going from +6 to +3. That means it has to be gaining electrons. So let's remember, Leo the line says GR. So that is our reduction reaction. Our carbon is going from -2 to +4. That means it's losing 6 electrons. So here's our Leo, our oxidation. So we're going to look at each half reaction. It doesn't matter which one you start with. I'm going to start with the reduction half, where our dichromate, and I'm going to leave a big old gap because we're adding a bunch of stuff and I don't want to run out of space. Goes to our chromium ion. You could also just put it in the center and add stuff on either side. Let's start with the easy stuff. Let's balance what we can quickly. We have 2 chromium on the left, so we need 2 chromium on the right. The next, because this is acidic, we're going to balance oxygen with water, and then we're going to balance our hydrogen with H+. So if we need 7 oxygen on the product side, we're going to add 7 H2O. That gives us 7 times 2, that gives us 14 hydrogen atoms. So we're going to balance that with 14 hydrogen ions. Now all of our atoms are balanced, but now we also have to balance charge. So if we talk about it, we've got +14 minus 2. That gives us +12 on the reactant side, and +6 on the product side. In order to make this balance out, we add 6 electrons. And now we have positive 6 and positive 6. So far we're done with reduction. Let's look at oxidation. We've got C2H5OH and carbon dioxide. Let's again start with the easier stuff and balance our carbons. And now we need to balance oxygen. We have 1 oxygen atom over here, but we have 4 over here. That means we're going to need to add 3 waters over here. I will tell you a hint. If you make water as a product in one half, it's probably going to be a reactant in the other half. The same is always true of the electrons, just by nature of what it means to be oxidized and reduced. Right? This one's gaining electrons, so it's going to be a reactant. The oxidation is always losing electrons, so it's going to be a product. Now we should balance our hydrogen atoms. We've got 5, 6, plus 6 gives us 12. So we have 12 hydrogen atoms. And let's balance our charge. There's no charge at all over here. On this side we have 12 hydrogens, so we're also going to have 12 electrons. Now we have all of our atoms and our charges balanced. At this point we're going to need to add them together. The problem is, before we can add them, we have to balance out the electrons. When we add these together, some of the hydrogens and some of the waters are going to cancel out, but not all of them. And this doesn't really matter because we know it's an acidic solution. So we know there are extra hydrogens and extra water molecules all around it. And if it doesn't quite cancel out, they're there present. We know that because we've said it's acidic solution right here. So that's acceptable. But we're never going to just produce or destroy electrons, and we can't just have free electrons floating around. So all of our electrons have to cancel. We produce 12 electrons. That means we need to have 12 electrons. In order to do this, we're going to take all of the coefficients in our reduction reaction and multiply them by 2. So now we have 2 dichromates and 28 hydrogens and 12 electrons, producing 4 chromium ions and 14 water molecules. There is one more step, is to add these together back into one line. So I'm going to scroll down so we have a little bit of space to do this in. And I'm just going to label it some because I like to label things. You don't have to. And you're just going to list it all out. Minus 2. We have our 28 hydrogen ions. There are 12 electrons. Now, before we go to these products, we've got to add these reactants as well. C2H5OH plus 3H2O, producing, and I'm just going to list it below, 4 chromium ions, 14 water molecules, 2 carbon dioxides, 12 hydrogen ions, and 12 electrons. Before we clean this up a little bit, we've got to cancel things out. We know that the electrons are going to cancel out. If they don't, then you've done something wrong and you've got to fix it. Let's look at our hydrogen. We have 12 here. That means we really only have 16 here. We have 3. That means we really only have 11. So we can recopy this for our final answer. And this is a good point to put back on those states of matter. That was aqueous. Plus 16 hydrogens, again aqueous, plus just one of these, it's a liquid, producing 4 chromium ions. Those are aqueous. 11 water molecules. It's liquid. And 2 carbon dioxides, which are gas. And there's your final answer. Now, if you wanted to, and you want to be 100% careful and sure, you can go back and double check your balancing. But if you followed your steps, it will be right. You've got 4 chromiums and 4. Got 14, 15 oxygen atoms, plus 11 plus 4 is 15. You've got 16 plus 6, you've got 22 hydrogen ions, and 22. You've got 2 carbons and 2 carbons. And it all balances out, and you can do the same thing with charge. -4 plus 16 gives us positive 12, and 4 plus or times positive 3 gives us positive 12. And all these steps have ensured that those electrons have gotten added. And I know this may seem like, wouldn't it just be easier to just balance it? But it doesn't work out because you don't know how many water molecules and hydrogens you need to add in order for all of that electron transfer to work out properly. Let's do one more acid example. This is again out of your book, problem 73A on page 174. I will tell you right now that the rest of question 73 is excellent as well, and all of the answers are in the back of your book. So I highly suggest them to use for practicing. Do at least one without there being a video and checking your answer. And if you don't get the right answer, just send me a message and I'll help you with it. You can tell that this is already written in net ionic form because there are ions. There won't be any ions if it's not already written in net ionic form, but you can always check if you wish. Otherwise, the next step is to break it into the half reactions, and to do that, we need to put in our oxidation numbers. So our zinc has an oxidation number of 0 because it's solid, and so does our diatomic molecule. Our ions are pretty easy. It has a -1 charge, so it has an oxidation number of -1. This has an oxidation number of +2. We know hydrogen is +1 if it's in an ionic compound. And our chlorine is also -1 again. So now we can break it into our half reactions. Our zinc goes from 0 to +2. That means it's losing electrons and being oxidized. Our hydrogen goes from +1 to 0, which means it is gaining electrons and being reduced. Let's look at our oxidation half first. Our zinc going to the zinc ion. This one's super easy. The atoms are balanced. The only thing you have to balance here is charge. We want to get rid of this +2, so we're going to add 2 electrons. Let's look at reduction. This we have hydrochloric acid and hydrogen gas. We have to add something else here because the chlorine is going to have to balance out. If you have ions not part directly of oxidation and reduction, but not just H plus or H2O, they're probably going to have to go with one of the half reactions, and it should work out fairly easily. Let's balance our atoms. We can put a 2 here to give us 2 hydrogens, and then a 2 here. we don't need to use oxygen because with this whole reaction, this redox problem does not have oxygen in it, which is really why this is so easy to balance. Single replacement reactions will always be easier because they usually won't have oxygen. So our atoms are balanced. Now we just have to look at charge. And we know that we have a product of electrons. So in reduction, when we're gaining electrons, they're going to have to be a reactant. We have a -2 charge here, so we're going to need 2 electrons. And you can see that we have 2 reactant electrons and 2 product electrons. So we do not need to multiply any coefficients. Next step is to sum them up together. We'll scroll up just a little bit. All of our reactants, zinc and hydrochloric acid and electrons, and zinc ions, electrons, hydrogen gas, and chloride ions. Let's cancel out the similar things. We've got our electrons canceling out, and that should be it. So we can write our final answer with those states of matter added back. Our zinc is solid. Our hydrochloric acid is aqueous. We're making aqueous zinc ions. Gaseous hydrogen. And aqueous chloride ions. And again, you can count the charges and all of that and make sure everything balances, but it will work out if you followed all your steps. So you can see that these problems can range from being really pretty simple and possibly being able to be done without using the half reaction method to being really complex. Now remember, if I'm asking you to balance a redox reaction using the half reaction method, you must do it this way. I must see this work, even if you could do it a little bit more easily without all of this work. I'm going to do the basic reactions in another video because the steps are slightly different and I want you to be able to reference them a little bit more quickly. But please try at least one practice problem and let me know if you need help.